In this fifth session of the module, I'm going to be talking about scheduling and project monitoring. So resource scheduling rather and project monitoring. And so what I'm going to focus on here is really in the first part of it, and really the bulk of the session, I'll be talking about optimization of projects really. So we've got the plan's in place. How can we optimize this plan to get it within a certain budget, within a certain time frame, and so forth? Also, I'll be covering a number of issues to do with that, and then in the latter section of the session, I'll talk about principally earned value analysis, monitoring the project, monitoring what's going on. Earned value analysis is a great way of reconciling cost and time, obviously two parts of the iron triangle, and I'll also mention briefly quality as the third dimension, but that's a bit more problematic, so I'll only just touch on that one. Okay, so the reading for this particular session is chapters 8 and 9. What I want to think about is the fact that projects are usually under some sort of constraint. So project managers have to revise the plan. The plan's there, they take the plan to senior management or have a kind of sense of what the expectations are. Then they have to revisit the plan, revisit the schedule, revisit the resource plan, and think about how they can get this within the constraints which they're operating under. So the scheduling problem. Projects are either, or tend to be either, time constrained in that they have to be completed by a fixed end date. They have resources which are add resources as required to meet the deadline. Here they focus on resource utilization. It's about smoothing demand. There might also be an issue around delay of non-critical activities by using Slack or Float to reduce peak demands and fill troughs in demand. Or they can be resource constrained. Resources can be people, materials, equipment, costs of other sorts. So here the project has to be completed within a fixed set of resources. Time is less of an issue, resources are the issue. The project may be delayed in order to keep within the resource constraints which are being imposed upon the project, and they might have to allocate resources so as to minimise project delay, but without exceeding resource constraints. Either way, schedules must be developed within the constraints that impinge upon the project manager and the organisation. So we have all these constraints which the project manager has to operate within, and at the planning stage these need to be taken into account. Okay, a little model to demonstrate this is out of Locke's book, I think. So this is a resource constrained project, resources are limited and time you can see is flexible, and this would be a time constrained project where time is fixed, resources become a bit more flexible. Yes, it's Locke's project management book. Okay, so constraints in the project schedule. So constraints can delay the start or completion of the project activities. Now this is a kind of can be a major issue for projects. Okay, resources can be increased to speed up project activities and project completion. So often project managers will, particularly if they're towards the end of the project and finding that they're behind schedule or not looking to, or suspect they may not achieve their time constraints, they can pile in resources in terms of people or additional resources of other sorts in order to get the project sped up and completed on time. Delaying or bringing forward activities can optimize the resource use in projects, so we can do what we call smoothing or leveling. Okay, and I'll talk about those briefly. And we can also do something called crashing, which is shortening the critical path, removing float from the project, loading up resources to carry out certain activities more quickly in order to get the project completed in a shorter period of time, or at least plan for the project to be completed in a shorter period of time. Okay, so the first thing to think about maybe is float. This issue of float or slack, I've used both words interchangeably. Um, because in normal discourse they're used either float or slack are used interchangeably. So project managers will talk about both, but mean the same thing. So we talked last time about float or slack being within projects, specifically on those activities which are outside the critical path. Okay, which means essentially that these activities can be shifted around a little bit around the schedule. So hopefully I'll illustrate that in a moment. Some activities can run concurrently, or they can be scheduled to run at different points in time. Float can be manipulated to optimize a project duration and the use of source resources. So we can reduce float or maybe possibly increase float, and this allows us to manipulate the planned project duration or the planned use of resources. Okay, let's think about a little example. This is out of Larson and Gray's book. It's the 5th edition, I think, but it doesn't matter. It's in the 6th edition as well. So in this particular example, we have a activity. You can see there's a series of activities down the side for this project, and this project is a kind of external work project, which requires something called backhoes. BH stands for backhoes. Okay, these are little JCB type diggers, and you can see that the first activity or design is carried out. Then the first activity, major activity, requires 2 of these machines, and then there's 3 activities which are scheduled to happen concurrently, and between them they require 4 of these machines. Then the next activity lighting, requires 1 of these machines, and then the final activity planting requires 3. Okay, so you can see there's an uneven distribution of these machines throughout the project, and you can see that shown there. So all I've done at the bottom here, underneath here, is stack up the number of times the resource is required, these machines are required, at different stages in the project. So the top diagram is a Gantt chart, the second diagram is a resource map showing the distribution of that particular resource over the duration of the project. So what we can do is shift a couple of one of the activities around. What I've done in this third resource chart is move a couple of the activities. In particular, if you look at the fence and wall activity, you can see that there's some float in this activity over weeks 10 to 16. So we could move that activity to start in week 10 and finish in week 16, and that would shift the requirement for 2 of these machines from weeks 4 to 10 to weeks 10 to 16. And so we have a smoother, notice the word, smoother distribution of resources, of this particular resource, throughout the project. Why is this important? Well, if you can imagine you have to maybe hire these machines or get them to the project site, then in the first resource schedule we'd have 2 machines, then we'd have to hire in 2 more machines to make 4, then we'd have to either keep those on site not being used, in which case they're a waste, or send them back to the hire company for some weeks and then so 3 of them would have to go back to the hire company for some weeks, and then we'd have to get 2 of them back again. This is kind of chopping and changing, or having machines or resources on site, on the project site, which aren't used. It's inefficient. Okay. Whereas in the second example, we have for the first up to week 10, we have 2 machines on site, on the project site, being used continuously, and then from week 10 to the end of the project, we get a further machine, and we have 3 machines on the project site for the remainder of the project. Okay, so hopefully you can see that this is a much more efficient use of resources throughout the duration of the project. That's why smoothing is so important. And here, what we've done is use float to shift one of the activities in order to create this smoother distribution of resources throughout the project. Okay, let's think about resource scheduling, and we'll go through this example. This is out of Larson and Gray's book as well, and it's called the Air Control Project. And you can see that here's a work breakdown structure for the project. We have activity number, a task, a duration for each activity, predecessors, so you can use these to work out a network, and then finally resources. These are individuals who are associated with different activities throughout the project. Okay, so we've got Ryan, Lauren, Connor, Carly, Dawn and Kevin. You can see initially that the critical path is 1, 4, 6, 7 and 8. What I've had to do, because of Ryan's limited time, he can't start activity 6 until he's finished activity 3, is shift that activity around. I'll move forward again. So that's what I've done here. So I've shifted the activities around and to accommodate Ryan's limited period of time. Here we are. So what we're doing in this case is leveling the resource. So I've had smoothing, now I'm leveling. We have a new resource constraint, not necessarily a logical connection, to connect the activities in a normal way. This is a resource constraint, which I've added there, and the critical path changes, as does the overall duration of the project. Okay, and this is the new critical path shown in the Gantt chart. So now activity 1 and 3 now, and then 6, 7 and 8 are critical, and activities 2, 4 and 5 are non-critical activities. Okay, this is shown in the MS project. You can see it's MS project. So here at the bottom here we have a resource diagram, resource graph showing the resources used in the project. Now, if you look at the little key at the side, you'll see that in the original project, Ryan was overloaded. We needed 2 of him for a period of time where his activities would have overlapped. So what we've done is reorganize this, and you can see it's shown in MS project again. Reorganize this the diagram, and now his time is 100% allocated throughout the period of time his activities are being undertaken. But in doing so, you've had to add some time in the project. Okay, there he is, Ryan, and there's his new resource constraint. Okay, so when resources are not capable of meeting peak demand requirements and are constrained, the manager has to. What does the manager have to do? The manager has to level resource usage, prioritise and allocate resources to minimise project delay. Okay, so this is important as well. We're adding time into the levelling, often adds time into the project, but we have to prioritise the resources to ensure that we're not adding undue time to the project. If resources and people are over allocated, what else can we do? Maybe bring another person to take Ryan's role. Maybe outsource that piece of work to somebody else. Or consider crashing the activities. So we've added a whole load of time because we've had to level the resources. Maybe we can then go and crash the subsequent project. So let's think about crashing a bit. Okay, it's invariably inefficient to start activities at their earliest start time because we have peaks and troughs, as we've seen in resource usage. So we usually shift activities around in the planning stage to smooth and level those resource usages. It's often desirable to level or smooth the resource usage throughout the project, as I just said, sometimes via redrawing the network, more likely via adjusting project start times, completion times, and or crashing or lengthening duration times. And I'll talk about crashing in a moment. So what does crashing involve? We can crash time and we can crash cost. Okay, so we've got the combination of time and cost in this crashing activity. And what we're trying to do is reduce whatever plan we have for the project. We then produce that plan, produce a schedule, and then seek to crash it to reduce the duration of the project to something acceptable for our purposes. Okay, so we've got a number of factors there. We've got normal time, normal cost, crash time and crash cost, a little definition of each one. So a way of thinking about it is by using the cost slope. Let's imagine we have an activity. It's going to take 10 days, which would be normal time, and it will cost £400, which we would call normal cost. Imagine we want to carry it out in 5 days, which would be a crash time. We'd have to add resources to this activity in order to reduce the duration of the activity. We can imagine we double the resources. It would cost £800 in order to deliver it in 5 days rather than 10 days. So we can draw a line from the crash time point down to the normal time, normal cost point, and this becomes our cost slope. So this is a straight line. It's a proportional increase in cost for every day which we have for this particular activity to reduce this activity, and we can calculate the cost slope, which is simply crash cost minus normal cost divided by normal time minus crash time. In this case, £800, which is the crash cost, minus £400, which is the normal cost, over 10 days in this case, which is our normal time, minus 5 days, which is our crash time. You crunch those numbers, you get £80 per unit of time. So £80 in this case would be the crash cost per day. So let's think about crashing a project. The way to do this is to first of all produce the network, work out the critical path, and then ignore in the first instance all those activities not on the critical path. We select the critical path tasks with the lowest crash costs and crash those first. Here is a project. So we have 7 activities, predecessors which enable us to produce a network, a normal duration for each activity. You can see there's various number of days per activity, and a normal cost per activity. We also have additional information, a potential point to which we can crash the activity. So for example, activity 1, task A, can be crashed from 3 days down to 2 days. We have a cost for crashing that activity, £70 in that case, from £50. Okay, so let's produce that network. It's activity on the node. We have the activities organised into a network, and the critical path is A, D, F, G. Okay, and the project duration will be 25 days in this case, and the cost of this project will be £450. Okay, so I've put this into a spreadsheet, this project, and you can see that what I've done is I've worked out the crash cost per day for each activity. So let's take activity A again. The normal time is 3 days, normal cost is £50, crash time is 2 days, crash cost is £70. In this case, you can only crash the activity by 1 day, so we know that it's going to be £20 a day to crash it. Where there's a greater opportunity to crash an activity, we can work out the crash cost per day using the formula I showed you earlier. Okay, so we can see that activity A has a crash cost of £20 a day, activity B £40 a day, activity C £30 a day, and so forth. So we ignore initially B, C and D, those aren't on the critical path. G, if you look at the bottom, can't be crashed. Normal time is 6 days, crash time is also 6 days. So what we do is we look at the crash cost per day. Which one has the lowest crash cost per day? Answer is activity A, which we just looked at. We can now we can remove 1 day from that activity to crash it, and it can crash down to 2 days. That'll cost us additional £20 to the project. Okay, so we crashed that, it can't be crashed anymore. So I put a little asterisk against that particular activity to show that it can't be crashed anymore. and we've reduced the duration of the project by 1 day in doing so, and increased the cost of the project by £20 by adding resource or doing something to speed up activity A. Okay, so can we get down to 23 days? Well, the answer is yes, we can. Okay, go through the same process again. B, C and D are not critical, still not critical. G can't be crashed. A can't be crashed any further. So we've taken 5 activities out of the equation so far. The next lowest crash cost of the activities which we can crash is activity D, which, if you look at it, can be crashed by quite a few days. We'll crash it by 1 day in the first instance and see what happens to the project when we've done that. Okay, so the crash cost for 1 day for activity D we've worked out to be £25, and that will reduce it from 11 days down to 10 days. Potentially it could be reduced down to 7 days, but we won't do that straight off. We'll do this incrementally, redoing it every time to calculate and each time redraw the network to make sure that the other activities haven't become critical. And we can keep doing that day after day after day, taking days here, there, and various other places. D, you can see, can actually, in the rewritten network, redrawn network, be reduced down to 9 days in total. F will be crashed down to 4 days. C can be crashed down to 9 days. D and E will be 6 and 7 days respectively. And if we do this process over and over again, what we'll get down to is a duration of 21 days. So 4 days quicker than the original duration, but at a cost of £610 compared with £450. What we've also done is make every activity critical. Now, there's a number of factors here, a number of issues here. One, the cost slope. We're assuming a straight line cost slope, that you add a bit of resource and you get a commensurate saving in time for that activity. Clearly, resources don't come in nice, smooth amounts like that, incremental amounts like that. A person might have a massive cost on the project to reduce the duration of an activity, but then they could reduce the activity by, say, 1 day or even 5 days. The cost slope itself can be critiqued because it assumes a nice, linear, smooth, incremental change in cost for savings. Okay. The other point here, the other important critical point, is that in crashing the project, we have reduced the duration of the project down to 21 days, but in so doing, what have we done? We've increased the amount of critical activities in the project. There's no float left, all activities are critical, and therefore we've increased, commensurately, risk. If something goes wrong in any of those activities that formerly did have float and therefore contingency, we have no flex in the project to allow for those sort of problems. Okay, and there's the cost to time saving chart which I can produce for the project which I've just looked at. So how can we crash the project? We can do all sorts of things, and so what you need to do maybe is think about some of these and how they might apply to specific projects. We could add additional resources. That's an obvious thing. In doing adding additional resources, normally we add additional cost as well. We can outsource project work, which is an option for some projects. Outsource it, again, is a cost increase, but it's getting someone else to carry out some of the activities. We can schedule overtime, again another cost, but increases resource, but without having to increase our manpower or person power for the project. We can establish a team, what's sometimes called a team concerted effort. Just everyone get on with it. A call to arms. We can do a quick and dirty attempt at trying to cut corners and do things which might not be giving us the best kind of outcome, but nevertheless get the project finished on time. and that's, as I said, sometimes works, sometimes infrequently doesn't. We can fast track by having activities running simultaneously rather than at different periods of time. So sometimes there's opportunities for fast tracking activities within projects by shifting them around a bit. We can brainstorm different options for time-saving ideas, sometimes called value management. We can reduce the scope of the project by taking activities out of it. We can phase the project, so we can have part of the delivery at one point and then carry on some work and then deliver another part of the project a bit later, often used in software projects, IT projects. Finally, we can compromise quality, do things more quickly, take shortcuts, source products and services which won't necessarily deliver us what we want, the quality we want, but will save us time. Okay, so there's lots of different things, and maybe you can think of some ideas of your own for how the activities on a project might be crashed. Potentially, you can keep going until all activities are critical. Okay. Okay, so that's the first part of the session. The second part of the session will be around project progress. So one of the key factors in projects is to understand the once we've got the plan in place, understand how we are, with the extent to which we're meeting the project plan as the project progresses. And this really is grouped in with the former section in this session, teaching session, because it's the last technical aspect of the project management, which I'm going to cover in this particular module. There are many other technical aspects, but I've talked about the critical path analysis. I've talked about PERT. I've talked about leveling and smoothing projects and crashing projects. This is the final part where I talk about project monitoring. Okay, so the reading for this particular aspect of the module is in chapter 13. That's where you can pick up on this, on this subject, on the topic of earned value analysis. Okay, so the bane of the project manager's life is changes to projects. These are essentially risks which are being realised in project delivery and create changes to our plan. Okay, so we have a plan of resources to be expended over the duration of the project linked to the project schedule. Okay, any changes will create an interruption to that plan. So the management project changes are an integral part of the project manager's life. Changes come from all sorts of sources, customer requests, which are external to the project normally, project failures of various sorts, such as functional deficiencies, slippage, cost variances, and also scope creep is a major factor, as we've seen in some of the examples we've looked at. So, what project managers have to do once the project commences is collect data. Collect data to monitor progress, to control the project. Sort of data you might collect. So budgetary cost versus actual cost. How much we plan to spend versus how much we've actually spent. People hours. Again, budgeted against actual expenditure. Budgeted percentage of completed of the project being completed, or the activities within the project being completed, compared with the actual percentage completed over a given period of time, and scheduled date of milestones against actual duration period of time when the milestone is achieved. Okay, so all measures require good quality data. So one of the key factors once the project commences to have some sort of people or number of people, or maybe the project manager, collecting good quality data which they can use to monitor the progress of the project. Some of the issues around the data: cost data is normally only available at the end of each accounting period, so often isn't in time for reasonable action to be taken. Man hours, or people hours should I say, I'll probably change that next time I think. It's normally accurate and up to date as timesheets are completed weekly. The percentage complete is subjective and optimistic normally. There's a certain bias which people have in assessing how much work they've actually completed, as I'm sure you can all testify to when you're thinking about your assignments. And milestones, which are always accurate but tend to be too late for any action to be taken. What are we doing in evaluating project performance progress? So the project manager needs to consider the performance criteria and they need to be monitoring things like time performance, cost or budget performance, and technical or quality performance. You can see that, and there's kind of a flex around scope in my iron triangle which I've drawn there. And they have to do all this in time to take corrective action if the project's going awry. Performance and project progress also need to be contextualised. What's happening in terms of the project and its delivery to organisational needs, and how is this project operating compared with other projects which might be being undertaken by an organisation. So how can we evaluate project progress? Right, it's a major concern to find some sort of visible means of reporting project progress. So the way project managers go about this, and this happens absolutely in all sorts of projects, it's really commonplace, it's embedded within project-based organisations, is to have a link between some sort of chart or diagram which often links expenditure, cost with time. So different ways of doing this. You can use the project network itself, very commonplace. You can look at incorporating the work breakdown structure packages into reports, use Gantt charts and control charts. Gantt charts and control charts are often used, and absolutely Gantt charts are just the basic method. You'll see this in project offices all up and down the land, around the world. The Gantt chart stuck up on the wall, printed out, stuck up on the wall, and often literally physically stuck up on the wall, and a big pen which is used to draw all over it to illustrate things that are going on, different risks that have been encountered, or different issues that they're dealing with, or problems they might encounter, and to also keep a kind of record of progress. So this happens all the time. They provide an overview, but they aren't particularly detailed, and the connection between cost and time is not very clear, often lost. Okay, the key one is earned value analysis. So let's talk a little bit about Gantt charts and their use. So this is the air control project I talked about earlier in the session. I'm revisiting it this time. Now we're looking at using it as a baseline Gantt chart and then mapping progress in the project against the baseline. So this is the same chart, and what I've done is I've got two measures there. You can see that halfway through the project, day 25, or a proportion of the period through the project, day 25, we take a snapshot of how we're getting on with the project. You can see some activities have overrun, and some have taken less time than we expected. The important thing is what's on the critical path, or if there's non-critical activity, whether it's used up all the float. So you can see that activity 6 is predicted to overrun because activity 4 was late, and activity 6 is dependent on activity 4 being complete. So activity 6 is overrunning because activity 4 was late, and this had an impact on the remainder of the project because activities 4 and 6 are on the critical path. Okay, so sorry, activity 3. Activity 3 had schedule. Activity 4 wasn't. Activity 4 was overrunning, and that's impacted on activity 6, and that has an impact on the entire project. Of course, this will allow the project manager to then do something. I'd say, well, we're going to be late, or they can say, right, okay, we'll intervene and do something to get the project back on track. Often done in MS Project. That's an example from MS Project. We can also use control charts. So this is sometimes used in projects, particularly things like software projects, things which have are regularly revisited on a day-to-day basis, have parts that are being handed over on a continual basis. You might look at whether it's ahead of schedule or behind schedule, and how far behind schedule the project is, and whether that means that we need to take action. Okay, action required. Right, earned value analysis. Now this is the big one. This is the very, very commonly used in projects. Okay, it's pioneered in the 1960s, widely used in the private sector. I've said that, but also commonly used in the public sector as well. Attempts to measure overall project progress. The process involves looking at the network, the original Gantt chart, the original network, the original cost plan, and distribution of costs over a period of time, and working out as tasks are undertaken how much expenditure we have over time. So this enables us to create the classic S-curve, and S-curve is very commonplace of expenditure over time, cumulative expenditure over time in projects. Okay, the percent of a task budget actually spent is not a good indicator of the percentage of the task actually completed. So that's just something to bear in mind. So there we are. Here we have a typical S-curve, cumulative cost, value or progress against our budget or plan, where we are and where we're projected to be. Okay, so let's think a bit about earned value. So it's a point-in-time evaluation. So these are often carried out on a regular basis, maybe weekly or monthly. We look at how much work we plan to complete, which is the plan value. We look at how much work has actually been completed, which is the earned value. And we look at how much we spent, which is the actual cost. Okay, so some of the definitions in earned value analysis. Earned value is the budgeted cost of work actually performed. So by budget I mean the scheduled or planned amount of work actually performed. So it's percentage complete multiplied by the original budget for the task summed over all tasks. The planned value is what we should have spent according to the budget, and the actual cost is how much is being spent. The best way to show this is through an example. So we have imagine we have a £10,000, it's a very simple example, we have a £10,000 software project. It's scheduled to be carried out over 4 weeks. At the end of the third week, we look at how much has been complete and how much we've spent. We discover that 50% of the project's been complete and that we've spent so far £9,000. So plan value is 3/4 multiplied by 10,000, 3/4 for 3 weeks out of 4. So in the third week, multiplied by £10,000, which is the budgeted cost of the project, which is £7,500. Earned value. We've completed 50% of the project, and the project was budgeted to be £10,000, so we've earned £5,000 of value. The actual cost is £9,000, as we know. Okay, so we can show this diagrammatically. We have a planned value or baseline, an earned value, how much we've actually achieved, and the schedule variance, the difference in how we're performing in terms of progress, is earned value minus planned value. Then we have an actual cost. And the cost variance, how much we plan to spend against how much we have spent, is earned value minus actual cost. So for both of these, schedule and cost variance, which are the two things we're looking at, is always earned value minus something, either planned value or actual cost. Okay, so the rules are all measures are taken on the same date. Negative variance is bad, so if it's negative, we are below where we want to be. Positive variance is, in inverted commas, I put it in inverted commas, you'll notice, good, in the sense that we're ahead of schedule or under budget. I say it's good, I'll talk a little bit about the critical perspective on that later. Okay, so we have cost and schedule variances which are calculated as earned value minus something, as I just said. Cost variance or schedule variance. You can see those there. So let's go think about what I went through is some examples. We have you can see diagrammatically that we have plan value. The plan value is the same right through these. I think the last one's not, but the first three examples are the plan value is the same. The last one is slightly different to demonstrate what's going on. And we have actual cost and earned value either side of this line. And you can see in the first one, schedule variance, which is earned value, is negative because it's below the line, and cost variance is also negative. Okay. In the next one, schedule variance is positive, cost variance is still negative. Okay, because cost is above what we plan to spend. Third one, schedule variance is positive, cost variance is positive because cost is below the earned value. Finally, schedule variance is negative, cost variance is positive. Okay. So let's go back to our example. We've established that the planned value is £7,500, the earned value is £5,000, and the actual cost is £9,000. So we can now work out the cost and schedule variance. Okay. Are we ahead of schedule? If so, everything's okay. Are we behind schedule? If so, then we're in problems. So schedule variance is earned value minus plan value. £5,000 minus £7,500. We have those two figures at the top. Leaves us a figure of minus £2,500. That's a negative number. We know we have problems in terms of schedule. We're behind schedule, in other words. But we knew that anyway. But in this example, we can see that in terms of figures. Cost variance is earned value minus actual cost. £5,000 minus £9,000 is minus £4,000. So we know we're overspending and we're behind schedule. Objectives metrics show that the project is behind schedule and over budget. Okay, so let's think about how we can compare this project against, say, another project, or this project against other projects might happen, or even give us a comparable figure. Okay, we use something called the schedule or cost performance index, and you can see that in this case we're no longer subtracting but dividing. So it's earned value divided by planned value for the schedule performance index, and earned value divided by actual cost for the cost performance index. Values less than 1 are bad, values greater than 1 are, in inverted commas, good. Okay, so go back to our same project. We now know that schedule variance is minus £2,500, and that means that if we take earned value and divide it by planned value this time, we get a figure of 0.66, below 1. Okay, we know that cost variance is minus £4,000. What's that mean in terms of a index figure? We now divide the earned value by the actual cost. That gives us a figure of 0.55, again below 1, highly problematic. So objective measures show it behind schedule and over budget. Okay, now that's not all we can do. What we can also do is forecast into the future. So given this position, can we forecast the likely cost to complete the project? Useful bit of information. We can report that back to our senior management, maybe use it to acquire additional resource which you might want, all sorts of things we can do with it. So the budgeted completion, the amount we expect to spend at the completion of the project, is the total budgeted cost of the task or project. In other words, the baseline. So what's the end point of the baseline? That's the budgeted amount of work we expect to have carried out at completion. Earned value equals the budgeted cost of work actually completed. Okay, the work remaining is the budgeted at completion figure minus the earned value. Okay, but so far our project, our cost performance index is earned value divided by actual cost. Okay, assuming the level of underperformance continues, then what's our estimated amount to spend to complete the project, etc. So we have work remaining is budgeted actual cost minus earned value over the cost performance index. So you can see why having these index figures is important. So let's do that. There's earned value, there's actual cost. Work remaining is budgeted at completion minus earned value, and then we have the actual cost. So we can put these figures into a chart to work out, into this formula to work out how much we have to spend to complete the project. So the total cost estimated at completion is going to be estimated at completion, whatever that happens to be, which is estimated to complete plus actual cost. Let's put that into our example. So there's the figures we have already. Right, the estimated completion is budgeted at completion, which was £10,000, that's what we plan to spend, minus earned value, £5,000, divided by our cost performance index, 0.55, is £9,091. So we expect to spend a further £9,091 to get this project completed. Okay, we have the estimated to completion, which is £9,091. Add that to the actual cost so far. We know we spent £9,000 so far. Gives us a figure of £18,091. So at the end of this project, we expect to spend, if it carries on as it is at the moment, £18,091 rather than the original budgeted £10,000. Okay. Let's go through another simple example. A task was expected to cost £1,500 to complete. It's due to be finished today. As of today, the cost is £1,350, and we estimate that 2/3 of it's finished. So, earned value, 2/3 of £1,500 is £1,000. Okay, we've earned £1,000 worth of value. The actual cost is, as we know, £1,350, and the planned value is £1,500. So the schedule variance is earned value minus planned value. 1,000 minus 1,500 is minus £500. Okay, so we know we're behind schedule. The cost variance is earned value minus actual cost, £1,000 minus £1,350, which is minus £350. So we know we're behind in overspending. So we can look at the schedule performance index. Earned value divided by planned value. 1,000 divided by 1,500 is 0.67. We can look at the cost performance index. Earned value divided by actual cost. 1,000 divided by £1,350 is 0.74. We are spending more on the baseline than the baseline indicated, and given that we spent more, we have not made as much progress as we should have done. Okay, so let's look at the estimated to completion, which is the budgeted at completion, how much we plan to spend, which was £1,500, minus the earned value. So far we know that's £1,000, divided by the cost performance index, which we know is 0.74, gives us £676. So we expect to spend, by the end of this project, a further £676 over what we've already spent, which is £1,350. So we would anticipate spending £2,026 in total on this project if we carry on as we are. So earned value is an objective method of determining project performance instead of more subjective approaches like using baseline Gantt charts. It enforces the project discipline, tracking the project actual performance against baseline costs and baseline schedules. The estimate to completion calculation can forecast the true project costs on project performance to date. So using the project performance to date. Okay, so earned value, really powerful tool to understand what's going on. Now, I will just return very briefly to the point I made earlier about whether this is good or bad. Okay, so broadly speaking, if we're behind schedule or over cost, then that can be seen as being bad. We are in a problematic situation. However, now here's the interesting thing. If we're ahead of schedule, or under costs, is that necessarily good? What that implies is actually we've planned incorrectly. And in fact, bad also suggests we've planned incorrectly, because the reality is not bearing out our planning. Maybe risks have been encountered or haven't been encountered, which we try to incorporate into the plan, or maybe our planning is just poor because we haven't got the right information or good enough data to produce a good enough plan, which then raises into question what value there is in the planning process. How is this going to help anyone particularly if we aren't really very clear on how accurate that plan is going to be? The big problem being that project managers get held hostages to fortune based on the plan they produced. This is the thing which gets disseminated across the project group, across the project team, to customers, to clients, and generally out to the media, if it's a high profile project. So this is the sort of thing which then holds the project manager as a hostage to fortune. Highly problematic. Okay, so there's a little bit of critical insight for you. Finally, little bit, only briefly, I'm going to touch on quality. So quality can be regarded as a performance issue. Are we achieving what we plan to achieve? And a performance issue. Are we meeting expectations? And actually, most projects are a bit of both. So in terms of performance, we might use ISO 9000, which is a international standard for quality. We might use quality costing or non-conformance records. British Standard 6143 is quality costing. We might use causal analysis to work out what's gone wrong and why it's gone wrong, or if something's gone wrong, those sort of things. Okay, in terms of performance, what we're doing is measuring expectations. You can use that in all sorts of ways. Expectations for whom, what stakeholders are we interested in, against perceptions. And then think about whether we can manage up or down the expectations to match the perceptions of what we're actually delivering. Okay, finally, a little bit about what we need for a control system. So we need to define the important characteristics, what's important. We need to work out what's acceptable in terms of variation. We need to have some sort of measurement system in place. We need to make progress visible. Might think about visible to whom. Do you want the customer to know how the project's going? Do you want the client to know? The end users to know? Other stakeholders to know? Maybe we are transparent about what's going on in the project. Maybe the project manager chooses to conceal what's going on. Often it does happen. Okay. We need to feed back to team on how we're performing, and then the team needs to take action as appropriate, and we need to take corrective action where necessary to get the project back on track and on cost. Okay, some last points which you might want to think about in terms of what I've covered in this session. So, projects are subject to a range of constraints: technical, physical, and above all, resource. So, manipulating the timing of activities in the project schedule can help to smooth or level resources which are going to be used throughout the project, so we can optimize it in that way. And activities can be crashed to respond to different project priorities and optimize the project in that way as well. Okay, by removing float. All projects, but then the cost of that is to introduce risk. All projects are subject to change, so require collection of performance data to monitor actual progress against planned progress. We can use tracking control charts, which I talked briefly about, variance control charts, I mentioned those briefly, and then I focused in on earned value analysis. This is very commonly used in all sorts of projects. Also, most projects have some sort of means of measuring or monitoring how quality is matching against what they were hoping to achieve.